Okay, so what I just gave you were problems. There's some practice problems in the front, and then in the last 2 pages, there's some RNS configuration problems that you're going to use. I think it says A for R and B for S. On the last couple pages, it goes 1 through 31. So those are going to be due on, I normally make them due on Friday, but since we don't have class on Friday, they're going to be due next Monday. Okay, and I've already put that online and the due date, so it's going to be due next Monday. Okay. I'll give you back your exams. I'll post the answer key today. If you have any, my suggestion for the exams is go over, look and see if you can identify what you missed first, and then you can always look at the answer key and then come and see me. It's not that I don't want to answer your questions. I'm fine with that. It's just that if you can figure out what you missed on your own, that's going to help it stick longer for the future. So that's why I make that suggestion. Okay, so what we're going to do is we're going to finish up chapter 6 today and then move into 7 on Wednesday. I have updated the folders for Wednesday and next Monday so that on Wednesday I have SN1 reactions. It's chapter 7. I put a couple videos to go with the book for chapter 7. And so that's what we're going to talk about. And then we'll move into 8 after for Monday, a week from today. Okay. All right, but let's finish up and talk a little bit about the Mezzo. We want to be able to tell what a Mezzo compound is, identify a Mezzo compound, and then relationships between molecules, whether they are enantiomers, diastereomers, they are the same but they're not Mezzo, or they're the same Mezzo compound. And then also, how do you determine RNS configurations on some of these different chairs, Newmans, Fishers, and there is a video on that I did put in for into today's folder if you want to go back and look at that after class, or if I don't quite get to that. All right, so let's deal with the molecule that we had that I left you with on Friday that I will take. We started with A, and then we wanted to write a B, a C, and a D, exactly like we did on Friday. The only difference here was that there were 2 OHs on the molecule instead of like an OH and a Cl. So so I started out with A. What was up here? An H, and then I put another H here, right? So then what was over here? A CH3? And then the OH was here, and then was the OH here, and then the CH3 was here. Okay. What were the configurations on the top carbon, R or S? R? Does everybody agree with that? That it was R? Okay, what about the bottom one? Yeah. I hear both, R and S. Which one? We all in agreement it's R? Okay. All right, what would be, somebody give me a molecule B. Julia?
H on the top and bottom, and then OH there, CH3 across from it, and then next quarter so that CH3 and then OH across from it.
Okay. So what's the relationship between this A and B? They're enantiomers. Okay, they're mirror images. They're mirror images, so A and B are enantiomers. So configuration-wise, top carbon in B would be S, and the bottom carbon would be S as well. Okay? How about C? Somebody give me their structure other than A and B. Okay. Okay. That's different. That's a new structure. And then what about D then? For D, what would I write? Let's just go ahead and write the mirror image. So there would be a CH3, CH3, H, H, OH, and OH. Now, configuration-wise, for C, what was the top and bottom carbons? Top one is S and bottom one is R. I'll agree with that. And then that would make this one R and S. Okay, so what's the relationship between C and D? Maddie? They're Mezzo compounds. Anybody else want to throw something in? Description-wise? Yes. It has to deal with superimposable. Are they superimposable? Meaning, can I turn one into the other? Are they the same? Do they have the same structure? The answer is, what's the answer? Yes. Because if I took this molecule and I rotated it 180 degrees, I would end up with H, H, OHs over here, and CH3s here. So if I rotate that 180 degrees, that's what I get. Now, I still have my bold and dashed wedges in the same place because all I did with that molecule is I rotated it like that. I didn't rotate it like this. If I rotated it that way if I rotated it in the through the plane, then all the bold wedges would be, well, here's the easy way to do that. Okay, there is my molecule with my pen as my wedge. It's pointing towards you. If I rotate it this way, all the wedges are behind, right? They're all in the back. So all I did was just take it like this and do that with it. So that is now superimposable. They're superimposable, which means they're superimposable. But what else are they? They're also mirror images. So these are superimposable mirror image isomers. And they are the same structure. And that is the definition then of a Mezzo compound. It's one of the definitions of a Mezzo compound. So if enantiomers are non-superimposable mirror image isomers, and diastereomers are non-superimposable non-mirror image isomers, then superimposable mirror image isomers are Mezzo. So that's the definition of what a Mezzo compound is. But there's more to that, Maggie. They're non-superimposable because you can't, because the only way to get A into B would be to rotate them in the plane, and that would mess up the bold and dashed wedges. So there's no way to superimpose A and B. And there's no way to superimpose B and C, or A and C. But C and D are superimposable. So that's the definition of Mezzo, and one of the characteristics of Mezzo compounds is they must have chiral centers. So if you have a molecule with no chiral centers and it's superimposable on its mirror image, it doesn't have a name. It only has a name if it has chiral centers, and it must have at least 2 chiral centers. So when we look at Mezzo compounds then, some of the characteristics of Mezzo compounds is, number 1, you have to have at least 2 chiral centers. You need at least 2 chiral centers in that molecule. It has to be superimposable on its mirror image, but another characteristic of it, before you go that far, is that the molecule needs to have what's called an internal mirror plane of symmetry. And what that does is the internal mirror plane of symmetry cuts the molecule in half, so that the top half is the same as the bottom half, or left half, right half. It cuts the molecule in half. And then the 2 halves are the same by a mirror plane. So in this case, where would the mirror plane go? The mirror plane would go right here. So I can cut this molecule in half by putting this mirror plane right here. And so now the top half is the same as the bottom half. Okay. So in general, another way to define Mezzo compounds is that they have more than 1 chiral center and an internal mirror plane of symmetry. So either one of those definitions works. One's more specific characteristics, and the other one is just kind of a general definition of what it is. Okay. So when we cut the molecule in half with an internal mirror plane of symmetry, it will be Mezzo if it has chiral centers. Now, anytime the mirror plane of symmetry cuts through a carbon, that carbon is not chiral. Okay? So you can't have the mirror plane cutting through what would have been chiral carbons, because they're not chiral anymore. So if a molecule doesn't have chiral carbons and it has a mirror plane of symmetry, it doesn't have a name. Okay, is everybody kind of okay with that? All right, so I need to test that to make sure everybody is okay. So we will play the game Mezzo or not Mezzo. Okay. Okay, so here's 4 molecules. For each one of them, I want to know Mezzo or not Mezzo. Okay, so give you a few minutes to go through those. You can discuss, you can work with other people, you can work by yourself, check your answer. We're going to take them one at a time. Is it Mezzo? Is it not Mezzo? And we'll make, I'm going to ask you, so you can get your card. At the end of this. So I'll give you a few minutes. Mezzo, not Mezzo. What? Do I have an extra card? I probably don't. So you can share with somebody else and find your answers. So if you think you're going to cross and any carbons that your flame passes through are on So if you're so I'll agree with that. Do we think we have some answers? Yes, no? Okay, I guess we'll find out. So, we will take them one at a time here. Okay, for number one, or for this one, we'll call this A. Is it Mezzo or not Mezzo? A for Mezzo, B for not Mezzo. A for Mezzo, B for not Mezzo. Okay. I have 22 mesos and one non-meso. Does it have chiral centers? Yes. These are two chiral centers. How do I know that? Well, I've got an OH and an H. I've got a CH2 here, and I've got a C with an OH, so those are 4 different groups. So that's the first thing I need to check is, do I have 2 chiral centers? Yes, I do. Do I have a mirror plane? Yes. Where's the mirror plane going to be? It's going to be this way. So the mirror plane cuts the molecule in half so that the top half is the same as the bottom half. I don't have to flip. I don't have to rotate. It just cuts the molecule right in half. Okay, so this one is Mezzo. So A is Mezzo. Okay. Does that make sense to everybody? Okay, how about B? What's B? Mezzo or not Mezzo? Okay, I got 23-1 that it is not Mezzo. Two chiral centers? Yes. But now this that plane does not cut the molecule in half. Because in order to make, well, that's what's called the C2 axis of symmetry. I would have to rotate 180 degrees to get the OH lined up. So that is not a mirror plane. So B is not Mezzo. Okay? Everybody okay with that? So now let's go to C. Mezzo or not Mezzo? A, Mezzo, B, not Mezzo. Oh. So we have 10 Mezzos and 14 not Mezzos. Okay, you know what happens then? We discuss for a minute. Then we'll revote. Whenever we have anything close to being 50-50, we need to discuss and revote. Okay, let's go ahead and revote based on your discussion. Based on your discussion, do you keep the same answer or do you change it? Let's go ahead and revote. Mezzo, not Mezzo. We're now at 10:15. Okay, so everybody pretty much is locked into their answer, or if you switch, somebody else switched to equal that out. All right, somebody who thinks this is not Mezzo, can you give me why you think it's not Mezzo? There's 15 of you out there. Julia?
So if you divide it in half, you'd either have to go through the two chiral carbons in order to get the fold, or if you go through 2 bonds, the OHs aren't going to overlap. Like they're not going to lay on top of each other.
Okay, I'm not sure that I
like if you the bottom OH needs to be moved to the left one, like over there, if you want the OHs to overlap each other when you.
Oh, when I do a mirror plane?
But yeah, to be like mirror, like them to be dead there.
So if I drew that, is that a mirror plane? Okay. So is that a mirror plane? Are we all in agreement that that's a mirror plane? Are we all in agreement that there are two chiral centers, two chiral carbons in this molecule? Does anybody disagree with that? So I've got an H, an OH, a CH2, a CH2, but we need to continue on. CH2 versus C, not CH2, so going around the ring, if I end up in the same place when I go around the ring, then those two groups would be the same. But in this case, CH2 is CH2 tie. Next one, CH2, not CH2. So I have 4 different groups attached to each one of those carbons. So they are chiral centers. Now, which 2 carbons is the mirror plane passing through? It is passing through these 2. So anytime the mirror plane passes through a carbon, it is not chiral. But what about these 2 carbons right here? Are they chiral? Were they chiral before I passed a mirror plane through them? No, because they already had 2 CH2s. And so CH2s cannot be chiral. CH3s can't be chiral. The only thing that has the possibility of being chiral is CH and a quaternary carbon that has no hydrogens. So in this case, yes, that mirror plane cuts through those 2 carbons, but did it cut through my chiral carbons? No. So I still have 2 chiral carbons intact. I do have a mirror plane. So this one is Mezzo. Okay, so I have to take it step by step. I'm giving you problems that I know are going to test your reasoning right now. And so that's why I'm giving you these problems, because if it's not, well, I mean, I know I'm going to get sometimes close to a 50-50 on some of these. Or I might even get the majority with the wrong answer. That's okay. Okay? So in this case, that is Mezzo. So the mirror plane cutting through carbons doesn't necessarily make the molecule not chiral. It would only make it not chiral if the mirror plane passed through the carbons that I think are chiral. Because then a mirror plane passing through a carbon is no longer chiral. Does that make sense? Okay. So this one is Mezzo. So let's do D. So, what is D? Mezzo, not Mezzo? I have 18 mesos and 6 not mesos. Okay. Anybody voting not meso want to defend their choice of not meso? Joe?
Just like the one we just did, if we had the same mirror plane, then it would pull on each other.
Well, wait. There's a mirror plane. Well, no. Stick to your answer.
I thought you had to break through like going in between bonds.
Not necessarily. I mean, in C did we do that? We didn't go through bonds, right? For C, we went through carbons. Over here, we went through bonds. The mirror plane doesn't have a specific place where it has to go. It can go through bonds. If it does, it's not passing through carbons, so the carbons don't become not chiral. But if it goes through carbons, then those carbons aren't chiral. So there's a mirror plane. What mirror plane did you draw? The same one as the last one we did. Okay, but the mirror plane, did it go through the C's with the OHs? Like that? Like these? Like that? Like this?
Yeah. That is not a mirror plane because let me erase the first mirror plane, because that means the OH would have to be here. That's why we thought it was.
Because there's no mirror plane.
Yeah.
There's a mirror plane. Is there another mirror plane? Yes or no? Yes? How you want to draw it? Like an X. Where you want the mirror plane to go? You want it to go through these two carbons?
No. Make it like an X. So, yeah, right there.
Like that?
Yeah, can you do that?
No. If that's the mirror plane, then that means the OH would have to be here and here. In other words, you're basically, the other thing you're doing with the mirror plane is you're just folding around it. So if there's an OH here, it has to go through the mirror plane to the other carbon on the other side. So that one is not a mirror plane. This one's a mirror plane, and where's the other mirror plane? That's a mirror plane. Or am I wrong? Is that a mirror plane? What? I'm wrong. How am I wrong? Well, not if there's a mirror plane that passes through them, then they're not chiral anymore. Okay. That would be a logical conclusion. So if that mirror plane goes through those two carbons, they ain't chiral anymore. And if they're not, then the molecule's not chiral. Exactly. So if I chopped an O and an H in half, the left half of the H would be the same as the right half of the H. So in other words, you can chop atoms in half. I can chop a CH. If I had a CH3, I could chop it in half like that, so that the two H's on this side are the same and the H there isn't the same. So this is a mirror plane as well. I'm noting some skepticism. Okay, fine. For this chiral center, tell me if it's R or S. I'll give you a minute. Top one. The top one with the arrow pointed to it. Is it R or S? Okay, let's vote. A is R, B is S, and C is can't tell. And your hand cannot be in the figure. Okay, I've got 13 R's, 5 S's, and 7 can't tells. I think we need to have a minute discussion. So discuss with the neighbor for a minute, we'll revote. Okay, time to revote. Based on your discussion, let's revote. A, R, B, S, C, cannot tell. Okay, so now we're split into 18 R's and 7 can't tells. So did all the 7 can't tells, did you hold your ground? Okay. So let's look at this. Number 4 group, hydrogen number 1 group, oxygen number 2 group. Is it the group on the, is it right or is it, well, is it, let's call this right, the right side, and let's call this the left side. Is it right or left? Which one's group number 2? I'm not hearing anything. Hold on, let's take the first statement. It's equal. Okay? Are they equal? So CH2 versus CH2 tie. Let's move on. CH2 versus CH2. Still tied. Let's move on. Uh-oh, we ended up in the same place. So statement number 1 is correct. They're equal. Now, your second part of your statement was?
It doesn't really matter because you're going to go from 1 to 4, so you can put a right carbon as number 2 and a left carbon as
So you can put, so if they're equal, you can just choose a 2 and a 3?
Well, they're both like 2.5, so I...
Okay, I'll take that. I'll take that they're both 2.5, which goes back to the original statement, which was they were equal. What happens when 2 groups are equal on a chiral center? What that here? It's not chiral. Right? So if 2 groups are the same, it's not chiral. And so in a cyclohexane ring, what happens is that if you go around the ring and you end up in the same place, it's not chiral. It's not a chiral carbon. So if they're equal, like you said, I can't do group 1, group 2, group 3, and group 4. You chose the one on the right. Well, what if somebody else chose the one on the left? So those two groups are basically equal. They're the same. Now, how do I know this? This is a circular argument. How do I know that those two groups are the same? Because I can pass a mirror plane through those two carbons. So they're still the same. Okay. So in cyclohexane, I'm giving you this problem because we hadn't done something like this. So those two carbons are not chiral because they have a mirror plane through them. If you don't like that, you can try and do RNS, but you end up with a problem there. Two of the groups are the same. As soon as two of the groups are the same, the carbon isn't chiral anymore. Okay. So in this case, you have a molecule with mirror planes, but does it have any chiral centers? No. It doesn't have any chiral centers. If it doesn't have chiral centers, and it doesn't have any chiral centers in a mirror plane, so what? It's just a molecule. It doesn't have a name. It's got to have both. It's got to have mirror planes and intact chiral centers. But if the mirror plane goes through a carbon, it isn't chiral. So actually then, if I was going to name this molecule, if I was going to name it, the two chiral centers don't have RNS. But how would I tell somebody the relationships of the two OHs? What would I say about that cyclohexane? I would say it's opposite cis. It's cis. It's cis. Because in this case, the cis isomer doesn't have any chiral centers, and so cis. The trans, is the trans meso? Is the trans meso? No, because it fails both tests. Well, actually, it doesn't fail the one test. It does have a mirror plane of symmetry, but the mirror plane of symmetry does cut the molecule in half, but it has no chiral centers still. Okay. Yes. Hold on. No, cis and trans also refers to the cyclohexane rings, or any cycloalkane ring. So this is important. Cis and trans, going back to where we were for the last exam, cis trans not only refers to the double bond stereochemistry, but it also refers to the ring stereochemistry. So if two groups are above the plane of the ring, it's cis. Two groups below the plane of the ring, it's still cis. One below, one above, it's trans. So two bolds, cis. Two dashes, cis. Bold and a dash, trans. So cis-trans is used for both the rings and the double bonds. Olivia? So D is not meso. It is not meso. Okay. Okay, so we did not get to the RNS on cyclohexanes or Newmans or Fishers. I'll be more than willing to answer questions on that on Wednesday, but what I would refer you to is the video in today's folder that says determining R and S on cyclohexanes, on Newmans, and on Fishers. And I do have models in there to kind of show you how that's done. So I would strongly encourage you to take a look at that, because you're going to need to do that for these homework problems that are due next week. Okay? But also then for Wednesday, I would like you to read Chapter 7, go through the video if necessary, or watch the video, then look at the chapter. Doesn't matter, whichever way you learn best. But both resources are there. And then on Wednesday, we will talk about, we'll start with SN1 reaction, or SN2 reactions, and then we will talk about R's and S's if you have those issues, okay? If you have questions, post them on Piazza. Somebody did ask a question about Chapter 7, which I will go through today. Here's your exams.